Good afternoon, everybody, and welcome once again to gRPC Conf. My name is Easwar, and I'm a software engineer on the gRPC Go team at Google. And today I'll take you on a tour of load balancing in gRPC. So we'll get started off with a very high-level overview of what load balancing is, what options we have in this space, some very high-level details of load balancing in gRPC. Then we'll dive a little deeper into the client architecture and see where load balancing fits in. And finally, we'll get into the weeds and we'll look at the load balancing API in gRPC Go. So if you're like the most interesting man in the world and you run a single server, then load balancing is not for you. You can drink a beer and you can go back home. But for the most of the rest of us, we run multiple servers. We have multiple clients sending multiple requests to our servers. So this talk is going to focus on L7 load balancing or application level load balancing and not L4 load balancing. So in gRPC, load balancing happens on a per RPC basis and not at a per connection level. So the main goal of load balancing is to ensure that your client requests are distributed across your server backends in a fair and appropriate manner. And by doing this, it tries to guarantee that your service can be highly available, scalable, and that it can respond to client requests in a timely fashion. So we have two options for load balancing at a very high level, and applications have to make this architectural choice. So it's either server-side or proxy-based load balancing or client-side. So with server-side load balancing, you have your clients talking to a proxy, and the proxy talks to a bunch of server backends. An example of this would be a Google front end or something like an Nginx. So the advantages with this option is that the clients can be super simple because the clients do not need to know where the server backends are running. They don't need to know how many of them are running, how loaded they are, or anything about the server backends. They just talk to the proxy, and the proxy takes care of everything else. So in the same vein, you as the service owner, you are running the proxy. So you have full control over the load balancing that happens in the proxy. But the disadvantage here is that the proxy is in the RPC path. So it can become a bottleneck, especially for services that require high throughput. So the other option is client-side load balancing. And here, you have your clients talking directly to the server. So you've eliminated the proxy hop. So this gives you better performance. But this comes with a bunch of downsides as well. So now the load balancing logic is moved into the client. And so this makes for a thick and complex client. And in most cases, you want your services to be accessible to clients written in multiple languages. So this means that the same complex client logic needs to be implemented in multiple languages. And also, since the load balancing is happening in your client, you as a service owner need to trust that the client will do the right thing in terms of balancing load appropriately. The good thing here is that if you're using gRPC, you get all those for free because gRPC supports client-side load balancing in multiple languages, and you can trust the gRPC clients to do the right thing. So gRPC can be used with both server-side and client-side load balancing, but it's really with client-side load balancing where gRPC really shines. So the component that performs client-side load balancing in gRPC is known by different names in the different gRPC languages. It's called load balancing policy in C++. It's called load balancer in Java, and just balancer in Go. So in this talk, we'll mostly use the term LB policy to refer to them. So an LB policy implementation mainly consists of two components. One is the connection management component that actually receives the backend addresses from the name resolver, and it decides when and how to create connections to those backend addresses. The second one is the call management component. And this component is invoked for every request. So when an RPC is made by the client, the call management component actually chooses the subchannel or chooses the backend that will be used for that RPC. And we call this component the picker in gRPC. We'll see more about this. gRPC also supports a plugin architecture for LB policies. What we mean by this is that gRPC defines an interface for LB policies, and individual LB policies implement that interface and register themselves with gRPC at init time. And at runtime, gRPC actually selects the LB policy to use. So gRPC ships with a bunch of LB policies. And the plugin architecture that I just mentioned also allows you to write your own LB policies. But given how many LB policies we support, we don't expect you to have that need. But if you want to, you can very well do that with the plugin architecture. So the LB policies listed here are just a subset. We have many more as well. And if you're thinking about writing your own LB policy, please do come and talk to us. There's a good chance that we already have something that can work for you. If not, we'd welcome contributions for new LB policies as well. So let's go through a couple of examples. One is pick first. You've probably heard this a bunch of times in this conference already, but pick first is one of the simplest LB policies that all implementations of gRPC ship with. And basically what it does is it gets a bunch of addresses from the name resolver and it starts connecting to them in order. And the moment it finds one that is reachable, it uses that for all the RPCs. And the next one is round robin, which is in stark contrast to pick first in the sense that when it receives a bunch of addresses from the name resolver, it basically blasts and connects to all of them. And when it gets an RPC, it tries to spread those RPCs across those ready backends in a round robin fashion. Now here are some very high level guidelines on choosing an LB policy for your service. Now again, a lot depends on the requirements of your service, but these are like super high level. So if your clients are actually going through a reverse proxy, then pick first makes sense. Or if you want soft affinity, where you want all your client RPCs to reach the same server backend because the backend is caching some data specific to that client, then again, pick first makes sense. And in the case where your clients are producing very small load compared to the overall load on the server, pick first with randomized shuffling works. I don't know how many of you were in Paul's talk, but when he was discussing about making some hacks to make pick first work, and I was thinking like, oh, why are they not using the randomized shuffling? And then later on he mentioned that, okay, gRPC added that support and then they're going to use that. So in most of the other cases, round robin or weighted round robin would work for you. So let's dive a little deeper now and look at the gRPC client architecture. We'll see a typical client workflow and we'll see where the LB policies fit in. So the client application creates a gRPC channel and it gives it the target URI, which basically represents the server that it wants to talk to. And at this point, the channel is not doing anything. It's just sitting idle there until the client application either asks the channel to explicitly connect or it makes an RPC. And now the channel comes to life and it actually goes ahead and creates a name resolver. And it gives the target URI to the name resolver. The name resolver will go and do its thing, and it will come back with a bunch of backend addresses and something called service config. So this service config is a piece of configuration that controls or specifies how a gRPC client behaves when it's talking to a gRPC service. So this piece of configuration contains a bunch of knobs, but the most important one is it contains the name of the LB policy to use. And it also contains the configuration to be passed to the LB policy. So based on that, the gRPC channel actually creates an LB policy. So this is what I meant earlier when I said that gRPC will select an LB policy at runtime. So it then passes the addresses and the load balancing config that was given to it by the name resolver. And at this point, the LB policy will go ahead and create subchannels to those backend addresses. So a subchannel is actually a real connection to a backend server. And the LB policy will be monitoring the state of these subchannels, and it'll manage the life cycle of them. And at some point, the LB policy will return an aggregated connectivity state to the channel, and it'll also return what we call the picker. So the picker, as I mentioned earlier, is the call management component. Basically, it's invoked for every RPC to select a subchannel from the list of subchannels that are available. So when an RPC is made, the gRPC channel calls the picker. And the picker will look at the ready subchannels, and it will pick one based on whatever algorithm it uses or whatever policy it's using. So once a subchannel is returned to the channel, the RPC actually makes its way out of that subchannel. So this is like a high-level overview of where LB policies sit in the overall picture. Now let's look a little deeper into subchannel connectivity states. So we saw that a subchannel is an actual connection to a backend server, but it actually goes through different connectivity states during its lifetime. And the gRPC channel actually notifies LB policies of these state transitions. So all subchannels start off in idle. So when they are created by the LB policy, they all start off in idle, and they're just sitting there doing nothing. And then at some point, the LB policy asks it to connect. So then it moves to connecting. And based on whether the connection succeeds or fails, it moves either to ready or to transient failure. And for a ready subchannel, if the connection fails, it moves back to idle. And at this point, it's up to the LB policy to kick it to connect again. Otherwise, it will just sit idle there. Similarly, subchannels which failed earlier and are sitting in transient failure will go through a period of exponential backoff. And once the backoff expires, they again move back to idle. And at this point, again, the LB policy has to kick it to connect. And from any of these states, the subchannel can move to shutdown if the LB policy decides to close the subchannel. Okay, so now let's actually go and look at the API. Just a note of caution that the API is experimental in Java and Go. You are free to use them, but you just need to know that they're experimental and we can make some changes to them. It's not yet public in C Core. It's blocked on the event engine migration, but we are hoping that we can make it public very soon. Okay, so we're going to look at the gRPC Go API, and it defines a bunch of interfaces. So we'll get started with the builder interface. So this is the interface that every LB policy has to implement and register with gRPC. So this interface is the one that gRPC uses to actually build LB policies at runtime. So it has two methods, one to build the LB policy, and two is to return the name of the LB policy. So this is the name that gRPC will look for when it gets a service config which specifies the name of the LB policy. So the next one is the balancer interface. This is called load balancer in Java and load balancing policy in C++, but this is basically the heart of the LB policy implementation. And so this has a bunch of methods, but I've listed a couple which are the most important, and they correspond to events from the name resolver. So when the name resolver comes back with addresses and service config, the gRPC channel will call update client const state to give it that new state. And the LB policy is free to use that state in whatever way that it wants. Basically, it can decide to connect to those addresses immediately, or it can decide to do something else. And the second API is resolver error. Basically, when the name resolver comes back with an error, gRPC channel uses this API to notify the LB policy of that error. The next interface is what we call the client con interface. This is called helper in Java and control channel helper in C++. And this is basically implemented in the gRPC client. And the LB policies use this interface to communicate with the channel. So again, this interface has a bunch of methods, but I've listed a few of the important ones here. So the first one, new subcon, is used by the LB policy when it wants to create a new subchannel. And it can pass it a bunch of options that we'll look at in the next slide. The next one is update state. So whenever the state of the LB policy changes and it wants to generate a new picker and send that to the channel, it's going to use that API. And the last one is used by the LB policy when it wants to request like re-resolution of the name. For example, like if the LB policy was given a bunch of backend addresses and it wasn't able to establish a connection to any of them, then the LB policy might decide to ask the channel to re-resolve the name to see if the resolution now produces a different set of addresses. So to monitor the subchannel state, we have an API in Go where the LB policy can pass a callback when it's creating a subchannel. And this callback gets invoked whenever the subchannel state changes. So this API is a little different in C++ and Go in the sense that it's part of the subchannel interface itself. But the concept is the same, that the LB policies will receive a callback with the new state of the subchannel. The last one is the picker. So the picker has a single method called pick, and it's passed a few things. Basically, it's passed the full name of the RPC, and it's also passed any request headers that it might use to decide how to select a subchannel for that RPC. And one important thing to note is that the pick call must not block. Ideally, it shouldn't do anything that is expensive, because this is going to be invoked for every request. So any delays here would significantly increase latency for all RPCs. Now, the picker can return a result which can be one of the 4 types listed here. So the first one is complete. So this is the case where the picker can actually select a ready subchannel to service the RPC. The second one is queue. So this is the case where the picker can't find a ready subchannel, but it's working on getting one. Like for example, there might be a connection request that's ongoing. So in this case, the picker lets the channel know that it has to queue the RPC, and the channel will retry the RPC when a new picker is generated. The third one is fail. So in this case, the picker can't find a ready subchannel, and it doesn't see a way of finding one either. So it asks the gRPC channel to fail the RPC. So in this case, RPCs which specify wait for ready call option will be queued, but other RPCs will fail. But there's also this concept of retries, which was mentioned by Ivy in her talk. So there could be further retries, further attempts by the retry code. The last one is very similar to fail, but even wait for ready RPCs will fail, and there won't be any more retry attempts. So that's mostly all for the API. So let's take a quick, so we're actually, running out of time. So I just have a couple of slides, but which show like the flow of the API, but we can take questions instead of going through those slides. Questions? Oh.
When a channel is connecting to the many different subchannels, is that like cheap because they're all in the same zone? Is that part of the idea at all?
So that totally depends on the addresses that are returned by the name resolver. So if it so happens that the addresses returned by the name resolver are in the same zone, so gRPC doesn't control any of that. So if it is like whatever addresses it is given, it will try connecting to them. So if you want control over that, then you'll have to control the name resolver. So name resolver is also a component in gRPC that is configurable. So if you write your own name resolver to control the set of backend addresses that are given to a client, then you can do that. But as long as a client gets a set of addresses from the name resolver, it's going to treat them all the same.
Is that an optimization that many companies use, or no?
So the LB policy has a choice. Like there's no need for the LB policy to connect to all the addresses that it's given to. So it can decide what addresses it wants to connect to. For example, there are LB policies in gRPC where the name resolver adds certain extra attributes to the address, something like priority or zone and things like that. So in that case, when the LB policy understands those attributes, it can make that choice and say that, okay, this zone is priority 0 for me. So I'll try connecting to backends in that zone. And if I can't connect to any of them, then I'll fall back to the next zone and things like that. So all that is open to the LB policy. But if you're using something as simple as pick first or round robin, then they probably don't understand those attributes. So round robin will try to connect to all of them, and pick first will try to connect to them in the given order. But if your LB policy understands that and the name resolver specifies those attributes, then you have total control over how connections are made. Does that answer your question?
Yes, thanks.
Cool.
Can you talk more about the connection management subcomponent in the LB policy, like just an extension to this question? Will that help in configuring the connections made? Like if we want to reduce the number of connections to our server, let's say there are multiple clients and we want to optimize that layer. So how can the connection management subcomponent help you?
So again, each LB policy decides what it wants to do with the given set of addresses. So there's no compulsion that the LB policy has to create connections to all of them. Based on the algorithm that it uses, it might decide to do that, or it might decide to do something else. And like if you're using something like XDS to do your name resolution, you can do fancy things there and implement subsetting in your control plane and have it give the client only like a subset of your backend addresses. And at that point, like the logic in the client can become simpler.
Hi, is session affinity involved at all in the client LB layer?
So session affinity, we do have an LB policy which does session affinity, but I think at this point it's only implemented in Java. I might be wrong, but my feeling is that it's only implemented in Java and the other languages don't currently support it. But there is an LB policy which does that. Any other questions? No? Cool. Thank you so much for coming.